Hello, everyone. Welcome. And I'm Yeonju Kim, a paintings conservator, and thank you for joining us today for Lunch and Learn at the Newark Museum of Art. So today, the Lunch and Learn program is a part of Science Week. So Dr. Greg Smith will tell us the mysteries behind the art through his research of the artist Pigments, and also hidden stories about artworks and unmasked forgeries. I think we are still waiting for some participants. And so while just for a few minutes, I can tell you about our future program this week, celebrating the Science Week. And so tomorrow at noon, we are celebrating Juneteenth with the rhyme, lyrics, and rhythmic dialogue, and also closing the week with a happy hour at 6 p.m. Okay. Maybe I can start. All right. So during the presentation, you can leave your questions at using the Q&A section on Zoom and in the comments on Facebook. All right, so here I would like to introduce the Dr. Greg Smith. He is the senior conservation scientist at the Indianapolis Museum of Art at Newfields. He received a Bachelor of Science degree from Central College of Kentucky in anthropology, sociology, and chemistry before pursuing graduate studies at Duke University. There, part of his research was working in archaeological fieldwork in Israel's Galilee region. He also pursued his research in various places for his postgraduate training, including working on investigations of pigments at the British Library and the Victoria and Albert Museum in London, and another research at Brookhaven, and research cleaning issues related to artist acrylic emulsion paints. So this is actually one of the biggest fights for conservators recently, so thank you. So he did this at the National Gallery of Art in Washington, D.C. So before he started working in the Indianapolis Museum of Art in 2004, he was an assistant professor of conservation science at SUNY Buffalo State College. So before he started working at the museum. So now he is the senior scientist, and he also constructed and now operates a state-of-the-art research facility to study and preserve the museum's encyclopedic collection of over 50,000 works of art. He also has authored numerous articles for journals in the fields of chemistry and conservation, and is an avid speaker on the interface between the art and the sciences. So here, Dr. Smith will tell us the mysteries and, more importantly, the connection between art and chemistry, further science. So I will hand it over to Dr. Smith.
Yeah. All right. Well, thank you, Yeonju. Let me begin just by saying how much I appreciate this opportunity to be a part of the Newark Museum of Art Science Week, and take this opportunity to tell you a little bit about my field of cultural heritage chemistry, which really straddles this interface between the arts and the sciences, and also will touch on some of those important allied fields, for instance, forensic science, which I'll mention a little bit later. So as you heard, I'm the senior conservation scientist at the Indianapolis Museum of Art, and my focus for the presentation today is going to be on pigments. So being trained as a chemist, when I look at artwork in our collection, I can appreciate that artwork for its aesthetic value, for the stories that the artwork tells, for its historical context, but I also can't help but also think of artwork as a collection of chemicals. And so pigments are a great way to demonstrate this. So if you took a course in high school or maybe in college, a chemistry course, you might have seen a chemical reaction like this, which is the oxidation of iron to form iron oxide, Fe2O3, or what we would commonly call rust. And you might remember that the game that you played was to come up with these coefficients, and that would balance the elements on one side of the reaction with those on the other side of the reaction. But this red powdery substance, rust, that we love to hate, actually occurs quite frequently in the Earth's crust, and it appears as a bright red mineral called hematite. And hematite is one of the earliest artist pigments. So this would have been used by Neolithic painters when they decorated rock outcroppings and cave walls with reds and purple and maroon colors. And so pigments are definitely chemicals. And what I also love about pigments are their diversity. The sources where we get colorants are quite diverse. And so hematite would be an example of a mineral pigment. And so I've shown another example of that up here, a bright blue stone that is called lapis lazuli. So this in Persian literally means blue stone, and it would have been one of the most important pigments on the artist's palette historically, because unlike the common hematite, this was actually a very rare pigment. So it occurs very infrequently in the Earth's crust. In fact, we only know of 13 sites in the world that have produced lapis. And historically, there was one primary site in the mountains of Afghanistan. And so this was a very rare and valuable material, which was used by the most wealthy and prestigious of patrons, and also often devoted to religious artwork where it would be used in a devotional way. And so you can imagine in historic periods, this rare mineral being mined out of the earth and ground into a blue pigment powder. It would move across Central Asia, it would move across the Middle East, travel across the Mediterranean Sea into Europe. It would cross Europe to the British Isles, all this happening before even the medieval period. Now, just to the side of that, we have lots of colorants that are derived from plant-based material. And these tend to be organic-based dye stuffs. The image that I show here is a pile of madder roots. So the madder plant, you could extract a bright red dye, an anthraquinone chemically, that was called alizarin. And this gave you your bright reds in textiles like Persian rugs. It's the red in red uniforms from historic military costumes. And there are a myriad of other plant species which give us dye stuffs that can be used in textile or used for painters' pigments. And they give us a range of different colors, the blues, the yellows, reds, purples, etc. Now, a little more bizarre and exotic is the idea that we can actually get colorants squeezed out of animals. And so this may seem really odd. My image that I showed down here is actually a pile of dried cochineal insects. So these are tiny scale insects which will infest the nopal cacti in the American Southwest and South America. And if you squeeze these little bugs, the pregnant females will generate a lot of a bright red dye stuff called carminic acid. And that gets its name from carmine, that term for a bright, rich red. And again, this was widely used in textiles, but also made into artist pigments. Now, other examples of animal-based colors are equally bizarre. For instance, people would take elephant tusks and char those into a black, luxurious pigment called ivory black. They would collect the urine from cows that were fed a diet exclusively of mango leaves, and this would give you that warm, translucent yellow pigment called Indian yellow. Now, in modern day, the majority of our materials are synthesized. So these are chemicals that are produced in factories and laboratories. But this is certainly not purely a modern phenomenon. In fact, going all the way back in history, people have taken natural products and used chemistry to synthesize and create new colorants. And so I'll be talking about that a little bit more deeply here in a minute. But my example that I show on the screen are these brighter than bright day glow colorants. So these are colorants that came out of the 1930s, really hit their stride in the 60s and 70s, and they have this abnormal intensity. And that's because of a chemical phenomenon that allows them to give you a 1-2 punch of color. So these pigments will reflect light and give you color, and that's the way everything gives us color. But they can also take all the light that they absorb and convert that energy into the same color as the reflected light and emit that. So you get two punches of color that make these extraordinary bright luminous pigments eye-catching, and that's why we find them in fashion and in advertising. So we've talked about all of this diversity. We have historic pigments, we have modern pigments, we have organic pigments, we have inorganic, we have man-made as well as natural materials. And with all this diversity, we need a wide range of analytical techniques to allow us to identify and study these various colorants. And we're really lucky here at Newfields to have a 3,000 square foot analytical chemistry facility. We're stocked with about $1.5 million worth of scientific tools, which allow us to study the materials of art. And so we can do analyses to assist our conservators when they're doing restorations or treatments of artwork. They'll want to know what that artwork is made out of. We might also do analyses for our curators or visiting art historians, but now all of that analysis is geared at interpreting that collection. We can actually answer some of those important art historical questions. Who made this? How old is it? Has it changed appearance after maybe a century of degradation? And then there's also that really sexy topic of, is this even real or might it be a fake or a forgery? And finally, we use all these tools also to study the fundamental chemistry of artist materials. So we might be investigating what's the action of pollution on artwork, or how does this particular dye fall apart when it's exposed to sunlight? So down at the bottom of the screen, you can see the range of instruments that we use in the laboratory. We use a lot of microscopes that allows us to look very carefully at the artwork, but also to go in and on occasion take tiny samples from the artwork, something that might be a quarter the size of a period at the end of a sentence. And that tiny sample might allow us to do a handful of different analyses. We can study the fading behavior of artwork so we know how to exhibit it. We've got techniques which allow us to look at all of the different materials, including the plastics that are quickly filling up our collections of design objects. And so all of this, we're lucky to have at our disposal to assist in identifying these materials. Now, I talked a little bit about the diversity and the breadth of the pigment class, and yet this is not a static area. This is constantly developing and still a very dynamic area as new colorants are being introduced. And this, in fact, has a long history of innovation. And so we can build a timeline of colorants. And I've done that on the screen, just looking at one color, the color blue, and starting way back in the Neolithic period and bringing us right up to today. So if we go to the start of our timeline right here, you can see the colorant indigo. This is a plant-based dye. It's been used since antiquity. The Egyptians, for instance, used indigo, and we still use it today. In fact, the image that I showed down here is of blue jeans, because indigo is the colorant that's used to make your blue jeans blue. Next to that, we have lapis. We've already spoken about this luxurious pigment. It's been used since antiquity. If you didn't have the wealth to afford lapis, maybe for your blues, you would use something like azurite. Azurite, also a natural mineral, and you can see this beautiful specimen here from one of our paintings conservators. The blue azurite actually co-mineralizes with its sister pigment, malachite. Malachite, also a copper-based pigment, but green in color. Now, my next stop is Egyptian blue in 3000 BC, and this is one of the very first man-made colorants. And so some clever Egyptian figured out that if you took copper filings and you mixed that with desert sand, embalming salts, and a little bit of lime, and you baked that in a furnace, you got this beautiful blue pigment. And so most of the blue things that you see coming out of ancient Egypt are colored with Egyptian blue. And this wasn't just limited to Egypt, it was mass produced and shipped all over the ancient world. So we find this as far north as Northern Europe. Now, if we jump way ahead to the 1700s, we get a major workhorse pigment that was actually discovered accidentally, Prussian blue. They were actually trying to make another colorant, but their reagents were impure, and this resulted a deep blue color. that's not only used as an artist pigment, but it's the blue that you find in blueprints, those architectural drawings, as well as those early photographs that were blue in color called cyanotypes. Now, if we jump down 100 years later, we have another major development with cobalt blue. This synthetic blue is the blue skies of the Impressionist and post-Impressionist painters. About 20 years later, another workhorse pigment is introduced to the artist's palette, ultramarine blue. And I want to point out its formula you see here is the exact same formula as lapis lazuli. And that's because the French government had a competition. It was sponsored by the Society for the Advancement of Industry. And there was a cash prize given to any chemist who could synthesize lapis lazuli in the laboratory. And so that happened in 1828. Next, we have cerulean blue. That's the sky blue color, the baby blue color. Phthalocyanine blue in the 1930s. Again, serendipitous discovery. They didn't try to make a pigment, but they created this amazing blue color and recognized its value as a pigment. And then bringing you up to modern day, in 2009, chemists at Oregon State University were making electronics materials, and they were mixing together different compositions of yttrium, indium, and manganese. And one of those combinations was bright blue in color. And so they call this Yinmin blue. It's one of our most recent blue colorants. And Crayola Crayon, in order to celebrate this discovery, introduced a new blue color to their crayon box. They had a competition to name this color, and the name that won was Bluetiful. So this shows you this innovation that has happened, and we can actually make use of this. As you can see, certain pigments are introduced at certain time periods. And so if we're analyzing an artwork and we find a certain colorant, we can now put a date to that artwork. We know that it had to be created sometime after the discovery of that particular pigment. And I think I can show that with this example. This is a small, about 1 foot stone sculpture in our collection. It's an Egyptian Ushapti figure that would have been buried in a tomb with a mummy. And this magical inscription would bring this figure to life in the underworld to serve its master. And so, like I mentioned, Egyptian figures, Egyptian material that has blue, like this headdress, should be Egyptian blue. But we were doing a technical study of this artwork, and we used a technique, laser scattering. It's called Raman dispersive laser scattering. And you simply shine this laser beam onto those blue pigment particles. It's totally non-destructive. And you look at how the laser is scattered off that surface. It gives us a spectrum or a pattern that we can compare to a library of artist materials and identify the colorant. And we were very surprised to find that in this instance, it wasn't Egyptian blue. In fact, it was that rare mineral lapis lazuli. And that was really astounding to us because the Egyptians had lapis. They used it for sculpture. They used it for jewelry, for inlaying objects, but they never ground it up and made pigment out of it. They had Egyptian blue for that purpose. So this would have been one of the few instances where we've ever found lapis on an ancient Egyptian object. But you have to be very careful with lapis. So we took a tiny sample. You can see this is the end of a chemically etched needle, and it's got just a few pigment particles on it. And that's enough to do a number of different types of studies. But what we did with this pigment was we dispersed it on a microscope slide, and we looked at it under a high-powered microscope. And what you see up here are those pigment particles. They're tiny, rounded, intensely blue particles, and not a whole lot of other things in there. And what disturbed us is that this does not look like lapis. Down below, you can see what lapis looks like. Lapis is a crushed mineral, and so it tends to appear like shards of broken glass that are lightly colored, angular, and there's a lot of other things mixed in there because the rock, as you can see, it contains both blue lazurite, which is the pigment you want, but a lot of white stuff that you don't want, things like quartz and calcite. And so this was not lapis lazuli in the end. It turned out to be synthetic ultramarine, which you remember was first created in 1828. And so that told us that this Egyptian figure could not be real. It had to be a fake. Well, occasionally when these pigments are discovered, they can have a ripple effect, which will affect other industries, other fields. And that was certainly the case with this green pigment, emerald green. It was also called Paris green. This was discovered in 1814 by the chemists Russ and Sattler, and they were searching for a new intense green pigment. And that's because even though painters want to use a lot of green, nature doesn't give us a lot of good green pigments. They tend to be kind of dull in color or prone to changing. And in fact, most artists would mix a blue and a yellow together to get their green. And anytime you mix two pigments, you go down in intensity, you never get a brighter colored pigment. So they were wanting to create a pigment that was intensely bright and green all by itself. And what they found is if they mixed copper and arsenic with vinegar, they got this bright acidic green color called emerald green. And this became all the rage in art and fashion and decor. Now I'm showing a picture from our collection. This is by the post-impressionist painter Charles Laval, called Going to Market Brittany. And it's actually one of my favorite paintings in the collection. And you can see here in the background that bright green color is emerald green. And as a chemist, what I love about this painting is that all the pigments are incredibly toxic. So you've got arsenic in the greens, you have mercury in the reds, the whites are made with lead, and the yellows are made with chromium. So those are all of our toxic heavy metals. Now I mentioned that sometimes a discovery of a pigment can have a ripple effect. And because of the toxicity of emerald green, it was quickly recognized that it could be used as an insecticide and a rodenticide. So the people who made this pigment would sell out of one door to the artists and the decorators, and they would sell out another door to the exterminators who were trying to kill rats and bugs. And so here's an example of a little jar of Paris green poison. And you can see down here, it's made by the Acme White Lead and Color Works company. Now, we actually had an opportunity where some of our work could impact other areas. And that was when we were investigating this ancient Egyptian pigment, Egyptian blue, and the fact that we might be able to repurpose it as a crime fighting tool for modern day crime scene investigation. And that's because this pigment has a really unusual property that almost no other material shares. It's a glow in the light pigment. So Egyptian blue can absorb visible light, and then it can re-emit it as invisible near infrared radiation. Now, our eyes can't see in the infrared, but with special cameras, we can capture this emission from Egyptian blue. And we've used this in conservation for decades to study Egyptian artworks. So for instance, here we see a cartonnage or mummy mask, and you can see the headdress is painted in this blue color. Now, if we capture that with an infrared camera, this is the image that you get. And all of that Egyptian blue is now intensely glowing in the near infrared. But a conservator would recognize that certain areas, like down here at the bottom of the mask, are not glowing in the infrared. And that tells us that it can't be Egyptian blue. In fact, it tells us that this object was at one point badly damaged and the bottom of it was crushed. It was restored by a conservator so that to our eye, we can't tell the damage is there, but the imaging certainly identifies it. Now, what we thought is this might be useful for a problem we had heard about in crime scene investigation. So if you leave your latent finger mark, your invisible finger mark, on a surface that is either highly reflective or very busy and patterned, it can be very difficult to dust that with fingerprint powder and collect a good image of that hidden fingerprint. And so what we thought is this infrared luminescence may be really useful for that. So the example that I show here is a polymer banknote from Australia that's been handled. And then we took nanoparticles of Egyptian blue and dusted that surface. And when you image it in the infrared, the background goes away. The busy pattern of the dollar bill or the $20 bill goes away. And all you see is the fingerprint with all of its intensity and the whorls and the ridges. And so we published this in a scientific paper. In fact, in 2017, this was picked up by National Geographic, and there was a small story on it in that. Well, I think I've burned through my time, so I want to end by thanking Sylvia and Stephen and Yunjo for the invitation to be a part of Science Week. And I want to thank you for your attention. I'm going to stop sharing my screen, but I'm going to stick around and answer any questions that people might have.
Okay, thank you. Thank you very much. It's very, very interesting. So first, do you hear my voice well, or it's not distorted or something?
I hear you.
Okay, good, good. Please don't forget to leave your questions at the Q&A section on Zoom and the comments on Facebook. So don't be overwhelmed by the word science. Science is our friend. So first, while we are waiting for some questions, actually, I have a question. This is not really in the presentation today, but I can't really help asking you this question. I know one of your researches was about finding pigments on Van Gogh's painting. And could you tell us that story a little bit?
Yeah, so Vincent van Gogh was a painter in the late 1800s, and this was a time when there was a lot of activity in synthetic chemistry. Scientists were coming up with a lot of new colors that were being introduced to the artist's palette. And Van Gogh was perfectly happy to experiment with using these colors. One of them at the time was called Geranium Lake. It was a very vibrant, hot pink color. And it was based off of this modern dye stuff in that time period called eosin. And unfortunately, as it turned out, eosin is not very stable to light. And so it faded over time. And if you think of an artist like Van Gogh, who's seen as a master of color, because of his widespread use of this pigment, many of his paintings, the way we see them today, are not the way that they were painted. So we were looking at an artwork that actually is at the Cincinnati Art Museum. And in that instance, we know from a letter that Van Gogh wrote, he talks about pink flowers being present in this artwork. But when you look at it, there are no pink flowers. There are a lot of white flowers, a lot of yellow flowers, orange flowers, but no pink. And so we began a process of examining this fading phenomenon and trying to identify which of the white flowers used to be pink but faded, and which of the white flowers were painted white to begin with. And the tell here is that that pigment, Geranium Lake, contains an element bromine, and no other artist material from that time period contains bromine. So if we could use a scientific technique and analyze the artwork and find traces of bromine in a flower, we knew that it used to be pink and had faded. And so we were able to do that. There were 387 white flowers, so that was a lot of analyses. And in the end, about a third of them were formerly pink but had faded.
So it means the painting we are looking at is not real colors.
It's not the color that Van Gogh would have seen when he put down his paintbrush. They're still very vibrant canvases. Everybody loves the intensity of the color in Van Gogh works. But in many of these, you might have to imagine the color schemes being quite different, maybe even more vivid than they are today.
So was there any treatment or revive this painting going back to original color?
Not actually on the painting, but with the miracle of Photoshop, we can take the artwork and recolorize it to give people a sense of what the original colors might have looked like. And so you're starting to see that at several museums where they'll study artwork that is faded and then try to present either through digital projection, putting the color back in using colored lights, or by using
onto the painting.
Yeah, directly on the painting.
Yeah. Okay. All right, thank you. So yeah, actually, I really want to see that digitally process the painting. So here we have a question. Could you tell us if you have ever proven that a painting was a forgery when everyone else thought it was real? And also, actually, another question is slightly related. Have you ever found a forgery at the Indianapolis Museum of Art that they didn't know about?
Well, certainly every museum is going to have fakes or forgeries in that collection. There's really a full spectrum of authenticity from the autograph work directly from the artist, but then you also have the work of students, the work of the artist workshop, you have copies and homages, and then you have outright fakes that are intended to deceive. And certainly we have encountered that. We are working currently on textile that turns out to be fake. It has modern dyes in it when it's supposed to be from the 1800s. We had a painting in the collection that we worked with our European curator. It was a painting by the artist Alfred Sisley. In that instance, we did chemical analysis, but everything about the materials were accurate. So it seemed to be an impressionist painting. But when we looked at the artist's signature, Alfred Sisley was a famous impressionist, what gave it away as a fake is that the signature, the paint, went down into cracks that had already formed in the artwork and then back out of the cracks and then down into the cracks. So this was a signature that had been applied to an already very old painting. And so yes, we do on occasion encounter forgeries in the collection, and part of our mission is to make sure that we cull the collection of these fakes and forgeries, because we certainly don't want to put something on exhibition that we know is not the real thing.
Okay, so there's one quick question kind of related to this. Does your group at the IMA examine artworks to determine authenticity prior to purchase?
There are certain things that we can do. We often have to work with the dealer or the auction house to make sure that we can't go in and take samples from artwork that we haven't already purchased.
Yeah.
But there are a lot of non-invasive ways that you can look at artwork. And really the talent there is in our conservators, who simply with a hand lens can look very closely at an artwork and often can say, you know, there's a red flag here. I'm uncomfortable with this piece. And that just comes from their years and years of experience looking at artwork. So the curators have a great eye, the conservators have their contribution, and then sometimes it comes to the point of doing scientific analysis just to make sure the materials are accurate as well.
Okay, thank you. All right, there are many questions. One question, what was the most exciting project you have worked at?
Well, I've had the fortune of looking at some really great artwork over my career: Gutenberg Bibles, paintings by Vermeer, Van Gogh's. And so, you know, all of those works can be very exciting because of the name recognition and the importance of the artwork. But I have to say also, sometimes the most exciting projects might be a totally anonymous pot from a Native American artist, historic pot. And you may never know who that person is, but you'll see a fingerprint in the clay. And then suddenly you make that connection that this is a craftsperson maybe hundreds of years ago who never thought that their object would end up in a museum or that somebody would be you know, looking at it this closely. And so you have both the ooh-ah factor, and then you have those intimate moments where you just really feel a connection to people who lived a long time ago.
Mm-hmm. So there's one question. So how difficult or easy is to make stable, lasting colors today, given the myriad of colors available, such as indoor and outdoor paint? How safe or dangerous are they to our home environment and greater environment?
Well, certainly industrial hygiene is a big part of any industry that's producing art materials. There are standard approaches for testing the toxicity of artist materials. We're very fortunate today that we have a wide range of colors, many of them with incredible stability, so that you can have a car in Arizona that keeps its bright red color for, you know, decades. And so chemistry has been able to answer that call for bright materials, safe materials. Historically, that hasn't always been true. We have examples of pigments that have been incredibly fugitive that have faded, like the geranium lake. We have examples of artist materials that have been incredibly toxic, like the emerald green. But by and large, here in the United States, for instance, we have a wide variety of colorants that are safe, are stable, and allow amazing things to be created.
And some kind of coatings might prevent the fading, you think?
Yeah, certainly there are in some pigments. As an example, there are coatings that are applied to some inorganic pigments like ultramarine. So ultramarine is a fairly stable material, but in acidic or alkaline environments, it can be destroyed. And so the pigment manufacturers will actually put a micron coating of silica or alumina, glass essentially, around the individual pigment particles. And that is acting like a little shield for the pigment particles so that they don't get affected by materials and lose their color. So there's a lot of strategies and techniques like that that are used in modern formulations of artist colors.
So there's one question, is more related to conservation. So I have to. So for someone who doesn't have access to a conservator, is there any safe way to clean an oil painting at home? I wouldn't recommend. You can dust with a soft brush very carefully, because here we're talking about any pastel, any flaking. Sometimes you cannot see it, but they exist. So still, I would consult any expert first. Yeah. So.
It could also be important to mention that conservators also run private practices. And so anybody in the community can locate a conservator through the American Institute for Conservation and then go and have a consultation with that conservator and hire them to do the treatment of the artwork. So this is what many people in the world, conservators, do. They run their own businesses. So it's not just museums that have access to conservators.
Yes, yes, that's true. Actually, my background is a private practice conservator. So thank you for adding that. Also, there are so many questions. Okay, what is your favorite color?
My favorite color? It's always been green. And so I think that's partly why the emerald green story made it into this talk. Not only is that a fascinating pigment, but it's got that incredibly vivid, rich green color.
Okay, good. And I have a question about that lapis lazuli and the ultramarine finding. And then now if I remember correctly, the first you thought it was a lapis lazuli, but later you were realizing it is ultramarine with a different spectroscopy, different instruments. So first, why this was thought as lapis lazuli?
Well, the answer there is that lapis and ultramarine are identical chemically. And so many of our techniques will get tricked in the sense that they'll say it has the chemistry of lapis, but it also has the chemistry of synthetic ultramarine. And so ultimately that distinction comes from looking closely at the particles. And so chemically they're similar, but physically their shapes are different.
I see. So when you find some information, you never confirm that it is. You always
we like to have at least 2 bits of information confirming our results. So we rarely just take one analysis and say, we're done.
Okay. Sorry. So given the very focused nature of your work in the art world, are there other labs in our outside of museums who do work similar to yours? So it means other than museums?
Yes, there are. So there are only a handful of laboratories at museums in the United States, and they tend to be at the places that you would imagine, things like the National Gallery of Art, the Metropolitan, the Getty. But there are other scientists that, like conservators, operate a private practice where they will undertake a study of your artwork for a fee. And so again, you can find some of these scientists online or through the American Institute for Conservation.
So there's another question. On the Shopti figure, was there other evidence that the figure was entirely fake? Or could the ultramarine have been added by a modern collector or dealer?
It could very well be that the pigment was added to a carved sculpture that had maybe no decoration. We haven't done any study of the stone itself to identify if this is an Egyptian stone. There are people who can do that. We don't have that expertise here. So everything about it tells us that the decoration is fake. The hieroglyphics are not accurate. They're added. The pigments and materials used to give it color are modern materials. They're not ancient materials. But for that reason, we still have the object. It's not like we pitch it just because the colors aren't right. So yes, there is a chance that the substrate, the stone, could be authentic and just decoration added later.
Oh, I see. Okay. Also, there was another question that these days there's no more ancient pigments. Recently they only use synthetic pigments or modern pigments.
Well,
for example, some people still use Egyptian.
Yeah, you can buy Egyptian blue from pigment manufacturers. It's being recreated today. In fact, anything from a historic time period or anything natural is still essentially available today. And so there are a lot of artists who like to use those historic materials to create their artwork. They don't want to use modern versions of colorants. And so there's a market for that, and there are providers, Crim pigment, natural pigments, people like that who reproduce these historic colors.
Mm-hmm. Yeah. And this was partially we talked about at the beginning of the Q&A part. So thank you for this fascinating presentation. Do you have an opinion about the Rothko paintings at Harvard Museum that a few years ago when enhanced to return them to their original colors via projections?
So this, if you don't know this story, there were some murals that were painted by Rothko. They were hung where they got a lot of sunlight. And unfortunately, one of the pigments he used was also very unstable and it faded very badly. And so those murals were taken off display when they no longer reflected the artist's intent. And so there was a very big research project to try and understand what the colors used to look like. And then once that was figured out, they were put back on exhibition and they used projectors to add the appropriate color back onto the surface of the artwork. And so this was done in a very measured, careful way so that no further damage was done. But it gave people the chance to come into a room and see these actual objects, not simulacrums or projections of artwork, but the actual object with color put back onto the surface. And the nice thing about that is that we don't actually do anything to the artwork. So it leaves that surface in its existent state so that we're not changing the surface, but it gave visitors an opportunity to see that. And I regret that I didn't get a chance to go to Harvard and see this when it was happening. Mm-hmm. But That is an approach that's being used in conservation. It's kind of virtual restoration or virtual conservation. And I think we'll see that more and more, for instance, in paintings by Van Gogh that we were talking about. There may be the potential to add some of that color back in and give you some appreciation of what the artist intended you to see when you viewed their work.
So yeah, actually, because yeah, that's a very good word, the artist's intention. So that is always our focus, what he really intended. But many times what we look at is already beyond what that's his intention. But when the painting is changed to the original intention, the audiences, viewers have a heart attack because it's like it totally suddenly changed, and then they only remembered. It's kind of, you have sometimes I think you have whether you lose your memory, and then you wake up 2 years later, what happened during that year? So some kind of shock. But the so that's why I think this process was very nice, the process toward to the showing the artist's original intention. Okay. I think we can close up the today's lunch and learn. There are no questions, but I'm sorry, we have to so today, thank you very much, Dr. Smith, for giving us good stories. And then thank you for also our audiences. Thank you for joining us. And and please don't forget tomorrow at noon, our Juneteenth celebration with the rhymes, lyrics, and rhythmic dialogue. And also, there's a good way to close our week with a happy hour and Science Week edition. So we celebrate Science Week by discussing the behavior of liquids and gases. So please join us tomorrow at 6 p.m. So today I will say goodbye here, and then thank you very much.